Hey. Hello, everyone. Welcome to this talk. I'm Ali Julian, PhD student in Network Group, and today I'm going to talk about foundational cryptography for non-cryptographers. So I assume that you don't have any prior background in cryptography, but instead you are familiar with basics of probability and statistics. And feel free to ask questions if something is not very clear, and then I will stop and make things more clear. Okay, the agenda for today is to first is.
You realize that we don't have the camera activated, that you would have on Zoom to activate the camera.
Okay, sure.
Can you find the Zoom control panel?
Yeah.
Yes, the video feed activated.
Is it activated? Yes.
Okay. But somehow it doesn't show. How about you?
Yes, good. Thank you. Okay. So the agenda for today's talk is first I will introduce you the symmetric encryption scheme. I think all of you are familiar with, but then I will talk about perfect secrecy and its inherent limitation, the most powerful notion of secrecy, but it has two inherently limitations. The key you must use for encryption should be as long as the message, and the other thing is that for encryption you can use the key once. These are two inherent limitations. I will continue with the new notion of, not new, but modern notion of secrecy, which is computational secrecy. And we will see, if we have time, that how we can solve these, deal with these two limitations with perfect secrecy, and using pseudorandomness, we can solve these two problems. Okay. I think all of you are familiar with the symmetric key encryption scheme. The problem is very famous. We have two parties want to communicate, Alice and Bob. Both of them have a shared key K, and the thing is that Alice wants to have a message, but the channel is not secure, and they want to communicate over such a channel. So Alice encrypts her message with the shared key K here with the encryption function, and then send it to Bob, and Bob, having access to the encryption key, can decrypt the message and find the original message. So formally, an encryption scheme is a triplet pi with three algorithms, Gen, Enc, and Dec, where Gen algorithm takes a parameter as input. We call it security parameter, something like a length of the key, and it generates a random key, which is used by both parties. The next algorithm is Enc algorithm, which takes this shared key and a message, and then generates a ciphertext C. Okay, and the decryption algorithm takes the shared key along with the ciphertext and retrieves the original message. As you see here, I have used different notation for the output of any of these algorithms. The story is that we have two types of algorithms: deterministic algorithms and probabilistic algorithms. A deterministic algorithm, when you run it multiple times with the same inputs, it generates the same output. Here, the notation is a column equal. So it means that for the same ciphertext and the shared key, it doesn't matter how many times you run this decryption algorithm. Always you will get the same message. But with these arrows, we mean that the algorithm generates probabilistic output. If you run Gen algorithm several times, each time you will get different output, different.
Yes. I also have a question. here, if I understand correctly, symmetric encryption algorithm creates a different ciphertext each time you...
No, I will deal with that. But in general, encryption algorithms can be deterministic or probabilistic. And here, both in general, there are some deterministic algorithms and probabilistic algorithms. But we will see that why we need an encryption algorithm to be probabilistic. And there is a limitation. If it is deterministic, then security violates for some reasons. And we will see that. So in general, encryption algorithm is a probabilistic algorithm, not deterministic.
But notation question.
Yes.
Very basic notation question.
Yes.
So is your equal operator symmetric? Or can you put the M on either side of this equal? Because in your example, at the bottom of the slide, you put
yes.
M on the left side, and then you put it on the right side. Does it matter on which side it is?
It doesn't matter. Yes. Okay. The thing which we need from this scheme, encryption scheme, is that when it must be correct. And by correctness, we mean that if we encrypt the message M with the key K, and we decrypt it with the same key, we must retrieve the original message. So I talked about 3 different algorithms. Then we can talk about 3 different spaces. The set of all possible keys, I note them with this fancy K, is called key space. All possible keys are key space. And the set of all possible messages, which is denoted by this fancy M, is called message space. And the set of all possible ciphertext with this with this fancy C is called ciphertext space, right? So we have 3 different spaces, and from perspective of an attacker, everything seems random. We can define 3 different random variables. The capital K here is a random variable for drawing a key from the key space. Capital M is a random variable for defined over message space. So it means that the support of this random variable is message space. And also the capital C is a random variable defined on the ciphertext space. Okay? We have 3 spaces, 3 random variables, and then we have 3 different probability distributions. Yes?
Are we assuming all these spaces are finite, or do things get really weird?
No, in my case they are fine. Okay. So then, having these 3 random variables, we can define 3 different probability distributions. Okay. By dk, I mean the probability distribution for random variable k, dm for m, and dc for c. Is that everything clear? Here you can see an example. Suppose that 2 generals in an army may change some messages, but the message space is limited. So all possible messages are these 4 messages: attack, defense, escape, etc. Okay, and then our message space would be A, D, E, and R. Okay, and for any reason, which is not important for us, they use only 3 different keys: K1, K2, and K3. And the algorithm for encryption is something like this you see in the table. For example, if the message is R and they use the key K1, the ciphertext would be 1. Okay? So the entire ciphertext, as you see, the ciphertext space consists of 1, 2, 3, and 4. So we have 3 different spaces, 3 different random variables, and here you can see that the probability distribution for the random variable n, for any reason, is summarized in this table. 25% of cases, they communicate message A, 30% times they communicate message D, etc. And the key space also has this random variable, For 25%, they use the K1 and etc. Okay?
Did you just make up those probabilities or you derive them from your...
No. These are, they can vary for different situations. The same algorithm, the thing is that we can have the same algorithm with this table, but with different probability distributions.
So you made up that table?
Yes, exactly. You can imagine these numbers as P1, P2, P3, but and P4, but the thing is that they must sum up to 1.
Okay.
It's a probability distribution, and you can imagine every possible distribution for any of these two random variables. The thing is that having this table, this algorithm actually, and this prior knowledge of message random variable and key random variable, you can calculate the probability distribution for your ciphertext. Here, as an example, we can calculate DC, which is distribution for random variable C, based on this table. So, for example, to generate C1, ciphertext 1, as you see in the table, we can generate it in the second column when the message is D and the key is K2, or when the message is E and key is K3, or message is R and key is K1. Okay? The thing is that we assume that in almost all cases, message space and key space, these random variables defined over these two spaces are independent. Okay? Then we can use law of independence in probability, and then we can say probability that n is equal D and k is equal K2 is their production. Okay? If you plug in the probabilities I showed you in the previous slide, you can end up with these numbers. Okay? And then you can calculate this PC as you see in this picture. So the thing is that we assume that an adversary has all of these knowledge. I mean, this table and the prior knowledge is about message space and the key space. He knows all of these probabilities, and he can calculate this this table, PC. So till now, I talked about the scheme, its correctness, the probabilities and the spaces. We can define everything, but we didn't talk anything about the secrecy of the scheme. What does it mean to say that is this a scheme secure or not? So there are two notions of secrecy. One is the classical one, which focuses only on the algorithm, regardless of the power of attackers or things like this. We actually, the aim is to design algorithms which are inherently secure by themselves, okay, regardless of computational power of attackers. The other thing, the modern one, is computational secrecy, and first we will deal with the first one, dive into the first one. So, Shannon introduced the concept of perfect secrecy many years ago, and the thing is that the focus in perfect secrecy is that, as I mentioned, the algorithm itself is inherently secure, which means that it leaks absolutely no information. Okay, and how we can formalize this concept that it leaks absolutely no information? So as you see here in the formula, probability that we had some message n given a specific ciphertext doesn't change the point of view of the attacker about the message space. As an attacker, you have some belief about messages. For example, as you see here, this is prior belief of the attacker, right? Because, for example, they captured several times the messages were communicated over channel. For any reason, they know that this is the probability distribution of message communication. So you know this one. And the thing is that having any ciphertext, you should not be held by the algorithm, encryption algorithm, to change your belief. If the ciphertext doesn't help you as an attacker, then it means that this scheme is inherently secure. So this conditional probability must not change your prior knowledge about the message space. In other words, distribution for n given c is equal to distribution prior knowledge of distribution. So in this notation, what is our assumption about the computational power of the adversary? Have we taken any specific assumption? In the formulation, there isn't any adversary. Okay, then it means that we assume that adversary has unbounded computation power. Okay, we assume actually implicitly that the adversary can compute whatever he or she wants. Okay, then the adversary is unbounded. As an example, let's review our previous example. Is this example a perfect secret encryption? Don't see this formulation and just focus on the table. Is it does this help the attacker? Yes?
No, it's not. I think one example is in A. So if the message is A, we know the cipher can't be 1. So that's some information we get from the cipher about the message.
Exactly. Or vice versa. If you have a specific ciphertext, let's say I have captured as an eavesdropper, I captured that message is 4, C equal 4 on the channel. Okay? Then having this table, for sure, I know that the message could not be R. In other words, message, the ciphertext is leading me to find some clues about the message, which was encrypted. Okay, then obviously it is not perfectly secure. So we can calculate, for example, this conditional probability. If I have seen C equals 4, then the probability that message is A is using Bayes rule, you can calculate that it is this one. For D, E, and R, you can calculate and see these probabilities are different from these probabilities. It means that the algorithm is changing my, my belief about the message space. That was, let me get back. It is a negative result, but is it the case for all possible encryption schemes? Even with limited like this, can you think that how can I modify this one, this very limited encryption algorithm to become perfectly secure?
Could you add one more key?
Definitely, we will see that in a theorem that it is impossible where the number of keys is less than the message space. It is not possible, but it is not sufficient. If you change the table with four keys, and then if in any row and column you have a specific permutation of numbers 1 to 4, then it is perfectly secure. You can check it yourself. Yes, please.
Is the space of ciphertext allowed to be strictly larger than a set of messages?
How it is possible?
Some key could map A to 1, another key could map A to 2. And if A is the only message, then I just created a cipher space that's larger than the message space.
Maybe. I should check that. Yes, please.
So then, how do you combine it?
I think the more important question is, whenever you have a perfectly secure scheme of that kind, can you reduce it down to one where the spaces are of equal size?
Yeah, I think that's what I wanted to get to too, yeah. That if you have linear combinations of the keys, you don't have more.
Yes, it's just that the definitions of the spaces didn't specify that constraint. You definitely need a cipher space that's at least as large as the message space, right? But is just bound on the other.
Otherwise, you cannot retrieve the original messages. Yes. Okay, but we know that there is a very famous algorithm which is perfectly secure, one-time add. And it is very easy. The message space is here, as you see. But by this notation, we mean set up all possible p-bit strings or p-bit numbers, anyway. And our message space is this one, and the generate algorithm generates a key from the same space, a random number from the same space. And the only thing the one-time pad does is that XOR the message with the key. And for decryption, the only thing we should do is to XOR the same key with the ciphertext. As you see here, this circuit takes a p-bit message and p-bit key and XOR them and generates the ciphertext. We can use the same circuit to decrypt the message. And the correctness is easy to prove. Decryption of encrypted message must be retrieve the original message. And here the decrypted message is K XOR with M. And if you XOR it with the K, decrypt it, these K's cancel and you can retrieve the original message.
Right. And does everybody know the XOR operation? Okay.
Good. And we can prove that this is perfectly secure. And I won't cover that here, but you can see it in the slides. Okay, so with a very basic and simple algorithm, we can achieve perfect secrecy, which is the strongest possible notion of secrecy. But why we don't use that in our regular work? Because not only one-time add, but also any possible perfectly secure algorithm has two inherent limitation. The first one is that each key cannot be used more than once. If you use a key twice, then you definitely reveal some information. For example, let's consider this situation. You have two messages, M1 and M2, and you encrypt them with the same key in a one-time. Okay? So C1 is equal to M1 XOR with K, and your second ciphertext C2 is equal to M2 XOR K. Attacker has access to both this C1 and C2 because the channel is not secure. Then he can eavesdrop cipher 1 and cipher 2 and XOR them. Right? If he XOR them, he's XORing M1 XOR K with M1 XOR K with M2 XOR K. These K's cancel out, and the remaining is that attacker knows what is the XOR of the first message with the second one. And so what? Is it leaking some information?
Yeah, it's not a random distribution anymore.
Yes, and the thing is that attacker now knows in which bits M1 and M2 are different. Okay, and he can force in real situation. He can force the sender to encrypt a message like 00001, and then XOR it with the target message to retrieve the first bit. 00010, the second message, the second bit. Okay, and this way you can reconstruct the entire message. Okay. So this is a real limitation, inherent limitation. And the second one is that the length of key space must be at least equal to the length of message space. Why this is the case? Imagine this situation. For simplicity, suppose that we have these three spaces, M, K, and C. Okay? I have the ciphertext C and two possible keys K1 and K2. If I decrypt this message with all of these two keys, then at most I can only retrieve two messages because the number of keys is less than the number of messages. Okay, then for sure I know, having this C, that M3 cannot we generated, retrieve. Okay, then this is leading the adversary and his belief about the prior distribution of message space will be changed. Okay. So yes.
How does the concept of weak keys come into the discussion? If you have a all zero one-time pad, the ciphertext is the same as the clear text.
Yes, but let's get back to our definition of one-time pad. Here, we suppose that the key is generated randomly. Although 0000 is a possible output, but attacker doesn't know about the key. Okay, and his assumption is that it is completely random key.
In particular, if the key space and the ciphertext space are of equal size, then every ciphertext looks like the plaintext, whether it actually is that plaintext or not.
On the other hand, if you see the ciphertext saying attack at dawn, it's very unlikely that was the outcome of two random things.
Yeah, but the sole model that we use is kind of unrealistic, right? Because we're just saying we have a set of 4 things, right? So attack at dawn would just be 0, 0, and retreat would be 0, 1, for example.
Okay, so escape, so it seems the framework, at least. Yeah.
Okay, knowing these inherent limitations, we can go one step further and define a new notion of secrecy, which is computational secrecy. This time, instead of focusing only on the algorithm, we make some real assumption that that our algorithm in real world are PPT, stand for probabilistic polynomial time, which means that our computation power is limited. So we know that our machines are inherently sequential. Most of them are sequential, which means that our algorithms are step by step, and they solve problems, only a subset of all possible problems, the problems which are from complexity class of polynomials. In big O notation, they are on O of Pn, where Pn is a polynomial. For example, an algorithm with time complexity of O to the n for n equals 1000 takes maybe a million years of time to be terminated. So our machines also can generate some independent and unbiased random bits in general. So they can be probabilistic. So in general, our machines are probabilistic polynomial time. And in general, our algorithms consist of, in our cryptography world, consisted of sender, receiver, and also adversaries. So all these parties are limited to PPT algorithms. To deal with computational secrecy, we need the notion of negligible functions. A negligible function is a function like epsilon, which is defined from natural numbers to real numbers, if its growth rate is slower than inverse of any possible polynomial. Formally, for every single polynomial you can imagine, there must be some constant value n0 such that for n's greater than this constant value, this epsilon must be less than 1 over this polynomial. Is that clear? This function grows polynomially, but this one has the growth rate of less than this one. Okay, and the thing is that the important part is that first, we don't need a universal constant value. For every single polynomial, we can imagine different constant value. And the other important thing is that it is not necessary to have this inequality, all this inequality for all possible n's. it must be whole from somewhere, from n greater than that constant value. For example, consider this function f of n equals 2 to the negative n. It is a negligible function. It means that 2 to the negative n is less than 1 over n. You can find some n constant value. For that, this inequality holds. It is also less than this one, and any possible polynomial. Okay? So, why negligible function concept is important for us in cryptography? The reason is that if a probability of an event is negligible, then it means that the number of trials you need to observe the occurrence of that event is exponential. Okay, you must exponentially many times experience that event to see on average an occurrence of that event. Okay, for example, consider this function 2 to the negative n as tossing a coin n times independently. Then the probability that you see that in all the experience you see the head is 2 to the negative n if the coin is fair. Okay, then to see an occurrence of this event, you must experience in order of 2 to the n of this event. You need in this order of experience. And what does it mean? Why it is important? Let's get back to our world of computation. We know that our machines are limited to polynomial algorithms. This means that we can have experiences which happen in polynomially many times, not exponentially many times. And this means that if we have something that the probability of its occurrence is negligible, then an adversary or any other algorithm cannot see an occurrence of that in reasonable amount of time. Okay?
So can I try to reformulate it to see
Yes,
whether I
please.
understand correctly? So we want to capture what are the capabilities of a classic computer with a polynomial function.
Exactly.
But we make no assumption about how fast that is, what kind of optimization the CPU is doing.
Yes.
It would be captured by the constant. So we ignore it, and then we just say it's polynomial. And then
Asymptotically, we talk about the situation.
And then now we want to qualify the quality of our security scheme. And in order to qualify this, then we capture that with a bound that we call negligible.
Exactly.
That captures the fact that then maybe the adversary, even if he were using classical computer, the amount of damage he could do on our scheme would be negligible.
Exactly.
Because it will grow much slower than what he can gain by using a lot of computers.
Exactly. Yes. Thank you for clarification.
I also have a question.
Yes, please.
It's rather technical, I'm sorry. I was wondering about the word typical there in the last sentence. I guess my question is basically, is there a meaningful or any class of functions which is properly sandwiched between the polynomials and the exponentials?
Yes.
Asymptotically. Yes, there are?
Yes,
Okay.
yes.
I will ask about that after this talk.
You are completely right by that. But this is also not.
Yeah, it doesn't matter.
Yeah, yours.
I'm just curious.
Yeah.
Okay. So the next step is the core concept of my talk, which is computational indistinguishability. To go toward this concept, I need another concept, which is ensembles. Till now, I have talked only about regarding to probability. I talked about distribution of, for example, a key space or a message space for fixed length of messages or keys or anything. But imagine the situation that you have designed an algorithm and the algorithm can generate keys of length 1 2, 3, etc., and etc. Okay, this algorithm is not only dedicated to a specific length of keys. Okay, so if you set the security parameter, in this example, the length of key, to 1, then you have, for example, 2 possible outputs, 0 and 1. For this one, you have a probability distribution. If you set it to 2, then you have, for example, 4 possibilities. Then you have another distribution. For 3, another distribution, etc., etc. So we formulate this concept with probability ensembles. An ensemble is a sequence of distribution. We denote that with this strange notation. And n here is, you can imagine it as the length of key, but in general, security parameter. Okay? So it means that for different values of n, you have different distribution. Okay? And what are these distribution? Where are coming from? You have one algorithm, it behaves probabilistic. Then for its output, for every single output, you have a specific probability. It means that for this run, for this specific value of n, you have a distribution, right? So your algorithm generates different distribution, and we call to sequence of these distributions for different values of security parameter, the ensemble. And we call computational indistinguishability is the concept which is mapped to ensembles. Okay, we can talk about computational indistinguishability of 2 possible ensembles. We consider the situation you have 2 different ensembles, X and Y, and we call these 2 ensembles are computationally indistinguishable if a PPT algorithm or PPT adversary cannot distinguish between these 2 sampling events. So here is the situation. You have 2 ensembles. You start sampling from one of these 2. For example, you select ensemble X and you sample from this. And you let the adversary know the samples. If the adversary cannot guess you're sampling from X or Y, then we can say that these 2 ensembles are computationally indistinguishable. Is that clear?
So in practice, these ensembles would be sequences of ciphertexts of equal length.
We can use this computational indistinguishability in many different areas. You will see that, for example, in randomness, pseudorandomness, we will use that. It is not limited only to ciphertexts.
Okay, but if we did apply it to the symmetric encryption from the start, would that statement then be correct?
Yeah. So, but there is a tricky point here. In this formulation, first, I wanted to be sure that these 2 probabilities is understood correctly by you. So the probability that adversary can successfully guess that the sample S, where S is coming from this ensemble X, this probability of success is almost equal to this probability of success. Is that clear? He has limited computation power, so he cannot guess from which this sample is coming. The thing is that here,
but before you go there, just to clarify a bit the notation.
Yes.
So A is the adversary.
Yes.
And the adversary is an algorithm.
PPT algorithm.
And then this algorithm takes a sample as input.
Yes.
And then it will say 0 if it's one of the distribution or ensemble.
Yes.
And it will tell 1 if it's the other.
Exactly.
Okay. And then
if this one means that this S comes from this one. Okay. This is ensemble.
And both X and Y, they are probability distribution, and inside each of them,
which one? These ones or these ones?
That ensemble X And
x of n.
yes.
It is a specific distribution for a specific value of n.
Okay.
Okay, but in general, we are saying that S is coming from ensemble. Why we need actually this ensemble? Yeah, it is very important. As you see here, I have written this difference of these two probabilities is less than or equal to a negligible function. But negligible functions were actually negligible, not for all possible n's, but from somewhere. Right? So here, both sides, I have n. Okay? So then it means that this ability to distinguish between these two ensembles is not necessarily valid for all possible n's. From somewhere, the adversary cannot distinguish between them. Okay? And it is formulated by the concept of negligible and ensemble both at the same time. Think about this situation. For example, let's say AES, which is a famous encryption algorithm, can take keys with different values, different length of key, and encrypt with different length key. And the thing is that we know that, for example, if the length of key is 40 bits, easily can be broken. Okay, this doesn't hold. But from somewhere, for example, with today's computer architectures and computation power, 128 bits is secure. Maybe 2 years later, another n, like 256, is the valid choice. Okay? So all of these things is formulated in this single.
Well, a very basic question.
Yes.
So, in your sequence, you have a exponent n to d, and then you have like a subscript n.
Yes, I missed that in here. So it is a typo.
Okay, yeah, and now I'm even more confused because I realized the second one. So the subscript n in your x and y, is that supposed to be the exponent n in your first example?
Yes. Here, definitely, there is a typo. It must be x superscript n, and this n outside of these curly brackets.
Okay, because I thought I was supposed to extract some subset of that sequence and reason in terms of that.
This is a typo. Sorry about that.
There's a number of n defines the power of the algorithm, how much is secure.
N is security parameter in general.
And S is just a bit string of length n then?
Exactly.
Or of length polynomial in n, I suppose?
In general, it must be polynomial of n. Okay? But in our last example, AES, it is the same. Yeah.
But, and now I'm confused about another statement that you said, which is you try to explain why you have n all over the place, and then you wanted to connect that to the negligible function by saying it starts from a certain constant. So it may not be true for lower than that constant, but it will be true starting from this, and it will be true for any larger ones. But I still don't understand how that connects to your sequence notation.
Exactly.
So what are you saying?
Let's have a concrete example. Suppose that this neg n is 2 to the negative n. Okay, it is a negligible function. And this x and y here are two ensembles which are generated by a random scheme, encryption scheme, a fully random encryption scheme, and the other one is for AES. Okay.
Okay.
The outputs of AES for different values of keys. I mean,
so
the
one would be
different
completely random ciphers, and the other one would be AES.
Exactly. Okay. So for n equal 1, this inequality is that the ciphertext with length 1, random 1, and AES 1 is less than or equal to the negative n. Is that negligible? If n is equal 1, then it is half. Okay. The difference between these two probabilities is 50%. It means that the adversary have the chance to distinguish between these two with at most 50% of time. So obviously it is not a good design. But if n is let's say, I don't know, 128 bits, then these samples are samples of 128 bits, and these are random 128 bits. The difference between them, between these two probabilities, becomes 2 to the negative 128, which is a very small probability. Okay, so on one hand, you have here a sequence of algorithms for 1 bit, 2 bit, 3 bit, 180 bit. So you have a sequence of distributions, and on the other hand, you have this negligible function which controls that which n is a good choice.
Okay, so let me try to reformulate it.
Yeah.
So what you're saying is you want to establish the security properties in the most general manner possible.
Exactly.
And maybe, but you don't know what the application is going to be. For a certain application, maybe you would need keys of at least 20 or 100 bits to be reasonable. But when you're designing the scheme, you don't care about this constant because you can just instantiate it for your problem, and then it comes from the person that's going to use the scheme.
And also, I don't know the computation power in a specific time.
Right.
Maybe this year with the next year are completely different.
Right. And you may have to increase this.
Yes.
But what you're saying is, even though I don't know what your requirements are in your final application, I just want to bound the fact that this, as the size of the keys grows, then the advantage that you get in distinguishing between those two ensemble probabilities grows less than the polynomial. It's negligible, and therefore there must exist a point at which it's usable because it will be small enough for your application. But I don't know that as a design. I just want to make sure that my scheme is valid at some point.
Exactly.
Okay.
So here you can see this notation I will use for computational indistinguishability of x and y, and also this one. Cryptography Society used strange notations, including this.
But they similar. That says exactly the same thing.
But the thing is that instead of writing sampling here, you can write it here.
Okay. But you're just saying that there exists two notations to say the same thing.
Yeah, exactly. Any questions? Yes.
I have a time question. How are we doing in time? How much do you need? Because we have a second talk. We want to bring before noon, right?
Okay. Yes, I will go faster.
But how much time do you need still?
I think half an hour maybe.
And that leaves half an hour only for your part.
That's okay. I will try to squeeze in, but in any case, I really.
I mean, it's really fast. I'm sure you can talk fast, but we can't follow faster.
But what you guys are not aware of is that Osman and Ali asked me yesterday whether they could rearrange a bit the time allocation in between the two talks, because Osman might have a bit less of content. He's not threatening to talk faster. Hopefully not.
Okay.
So I will raise the time awareness again in 15 minutes.
And I'll go start the rice. And I'll be there.
Okay, so as a very concrete example, consider this situation. This is an ensemble because parameterized by n. We can differentiate the value n, and for example, for n equal 1, you have 2 of these bars. For n equals 3, n equal 1, you have 2 bars. For n equal 2, you have 4 of these bars, etc. And the probability varies. My question is that suppose that this is x, ensemble x, and this one is ensemble y. Okay? And we have the PPT adversaries. Can the PPT adversary distinguish between these two ensembles? How?
By sampling maybe 2 times, so I don't know, and then seeing whether all of them are even.
Exactly. Not all of them, but let's say the situation is that you are sampling from one of these two, and the adversary sees these samples. At the first time, he can see an odd number. For sure, he can realize that, okay, you were sampling from this one. Although these probabilities are negligible, you see 2 to the negative n plus 1 is a negligible probability for large n's, but these are computationally distinguishable. Okay, if there is a pattern, then adversary can distinguish between them. But what about this one and this one? There isn't any pattern here. This is the situation. We are talking about this situation. Okay, so to wrap up everything, adversary needs exponential number of trials to be able to distinguish between two computationally indistinguishable ensembles. Yes.
Where distinguish means distinguish with a certain confidence?
Yes. In general, in cryptography, when we say it is distinguishable, we mean that the advantage of distinguishing is not negligible.
The advantage.
Even though, for example, if it is 1 over n squared, it is disaster in cryptography. So, now we are ready to go to the modern cryptography. And perfect secrecy was unnecessarily strong because we had somehow stupid assumption that the adversary has unbounded computational power. So in modern notion of secrecy, we think about real world adversaries, which are bounded by PPT algorithms on one hand. And on the other hand, with this formulation, we wanted that the algorithm leaks absolutely no information about the message space, okay? Which is also not a good idea. Instead, we let the adversary, the algorithm, to leak information, but with negligible probability. Why negligible? Because adversary is limited to polynomially many experiences, and we cannot realize this difference. So to go toward the formulation, let's recap the perfect secrecy. Our first formulation was this one, right? Probability that m equals m given c is equal to our prior knowledge about the message space. So in terms of the, so do you agree with me that we have different security parameter for both sides? So actually this formulation is talking about ensembles, and I can write it like this. Okay, with different values of n, I have this ensemble and this ensemble. We can prove, not that much complicated, but we can prove using Bayes' theorem that this first definition is equivalent to this one, which says that the probability of having a ciphertext given a specific message for different messages must be equal. Okay, probability that you see ciphertext C1 for M1 and M0 must be identical. Okay? In other words, probability distribution of ciphertext for a given message must be identical for another message. Okay, and how this probability distribution comes? We have different values for keys. Okay. Again, these two are two ensembles, and I can reformulate it as ensembles. And this one is equal to this one. Why? Because C distribution of C given m equals 0 means that to encrypt message M0. Okay, so encryption of message M0, and here we have probability distribution, which means that we are varying the key. Okay, for different values of key, I have this one. For different values of key, I have this one. And these two ensembles must be identical to this encryption scheme be perfectly secure. Okay. Our goal was to think about real-world algorithms, adversaries, PPT algorithms, and leaking a little bit of knowledge about prior distribution. what should I do with this to achieve these two goals? These two ensembles in perfect secrecy must be identical. And in modern cryptography, what do you guess about this equal sign?
You bound the absolute difference by a negligible function.
In other words, the template was computationally indistinguishable.
For example, plus epsilon.
Yes, exactly. That is the definition of computational indistinguishability. So then, if these two ensembles are computationally indistinguishable, instead of identical for all possible ends, then I achieved everything. Not for all possible ends from somewhere, for computationally bounded adversaries, these two are indistinguishable. And we can prove that this definition is equivalent to this game-based definition, computational indistinguishability secrecy. So, an adversary can select two messages with the same length from the message space and send it to the adversary. Send it to the challenger. Then challenger generates a key, uniformly at random selects a bit, and selects, based on this bit, selects either M0 or M1. Okay, so MB is M0 or M1. And then encrypt this MB with the key and send it to adversary. An adversary with bounded computation power tries to guess whether M1 was encrypted or M0 was encrypted, and then returns his guess to the challenger. Yes.
Well, technicalities. Messages suddenly have a length. They didn't before. So is this a notation that implies the choice of n?
Yes.
All right.
Yes, exactly. Exactly. So the gain value is whether b equals b prime or not, and the scheme is called computationally indistinguishable secure if the probability of winning this game, this means this is the experience, this experience is called prev k, it depends on a and pi as a encryption scheme, and 1 is when b equals b prime. The adversary can win the game. The probability that adversary can win the game is 1/2 plus a negligible. Why 1/2? Because always can guess randomly. And the next concept, till now, we know that there are two notions of secrecy, perfect secrecy and computational secrecy. And how we can achieve computational secrecy? We saw one-time hat for perfect secrecy, but what about computational secrecy? I'm going to introduce the notion of pseudorandomness. The behavior is not completely random, but similar to random. You cannot distinguish between random behavior or deterministic behavior. So, pseudorandom ensembles. In cryptography, by convention, we say that a distribution, an ensemble is random if the ensemble is uniform. Okay, instead of saying uniform, say random. And it is called pseudorandom if the ensemble is computationally indistinguishable from random distribution, which is uniform. Okay? Do you remember the definition of computationally indistinguishability? You sample from any of these two ensembles, and the adversary cannot distinguish, except for this negligible times. And here you can see that we are sampling from ensemble B, or we are sampling from uniform distributions. Okay, so if the ensemble is computationally indistinguishable from uniform ensembles, then we say that this ensemble is pseudorandom. So we can generate some functions we can define some functions that generate pseudorandom numbers. But before that, let's clarify something. This randomness and pseudorandomness in cryptography are not related to numbers or values. Okay, you cannot say this number is a pseudorandom number. It doesn't mean. This feature is a feature of ensembles or distributions. Okay, but in my talk, whenever I say that this number is a pseudo-random number, I mean that it is drawn from a pseudo-random distribution. Okay. So, a pseudorandom number generator is a deterministic algorithm from the space of n bit strings to p bit strings, such that we know that p must be greater than n. As you see in the picture, this is the input value and this is the output value. We call the input value c, and the length of output is greater than input. And if the output of our function g, we know that this function generates some values for different values of n and p. Okay, let's say n is the security parameter. Okay, this g generates outputs. For each value of n, we have a distribution. So in general, we have an ensemble. Okay, if this ensemble is pseudorandom, then we call that this function is pseudorandom number generator. And by pseudorandom, we mean that it is computationally indistinguishable from uniform distributions.
This last
The sentence was that this G generates, in general, any algorithm in cryptography generates a sequence of distributions. In other words, generates a ensemble. Okay, so here we have an ensemble. We call this function pseudorandom number generator if the ensemble this generates is a pseudorandom ensemble. In other words, based on the definition of pseudorandom ensemble, it is computationally indistinguishable from uniform ensembles.
What's the n and the p on the generator?
N is the length of the input, and p is the length of output. It scratches the length of our input. For example, you fed, I don't know, 10-bit inputs and get 100-bit inputs, for example. Okay.
Yeah, okay.
Okay. So let's get back to our limitation. One of our limitations was that length of key must be greater than or equal to the length of message. How we can solve this problem with the notion of pseudorandom generators? Easily. We had one-time path. Okay. The length of key with the length of message were identical, and we XORed them. Okay. But now we have a mathematical tool. We have this function. It takes short numbers and expand them to longer numbers such that a computationally, polynomially bounded adversary cannot distinguish this with this uniform random number. Okay, so as he cannot distinguish this with this, okay, then XOR your message with this one. And the problem is solved. The other limitation was that we could not use a key more than once. So to deal with this problem, we need another mathematical utility, which is pseudorandom functions. But what is
20 past 11.
Okay, in 10 minutes I will finish.
Good.
Okay, thank you. The other tool is pseudorandom functions. Similar to pseudorandom numbers, we had random or uniform distribution, and then based on that define random, pseudorandom numbers. Here also we have random functions. Okay? What is a random function? Imagine all possible functions we can define on this space, n bits to n bits. And I call this the set of all these possible functions f of n. Okay? For sure, each of them is a deterministic function. And how many of these functions are imaginable? For the first, for how many inputs do we have? 2 to the n inputs, okay? Imagine a table here with 2 to the row inputs. And the outputs, how many of outputs are possible? 2 to the n, okay? The first one can be mapped to any of these 2 to the n's. So for the first one, I have 2 to the n possibilities. For the second one, also I can map it to any of these 2 to the n's. So again, 2 to the n possibilities. Again and again till I have 2 to the n sort of these 2 to the n's. So in general, I have 2 to the n powered by 2 to the n or 2 to the n 2 to the n. Okay? So this is the number of functions I can define or imagine at least. Then I draw a function uniformly at random from this space or this set, and I call this function a random function. Okay? This is equivalent to this scenario. This problem set is equivalent to this experiment. To say that, okay, I have a table with 2 to the n rows. The first row contains value 0, the next one value 1, etc. The last one 2 to the n minus 1. Okay? Then a random function defines as following. When I queried to f of x, to calculate f of x, I check my table. If I was not queried by this x, then I randomly draw a number from uniform distribution and register the value for this x and return it to the person who asked f of x. And if I have already been requested for this f of x, then I check the table and return the same value because it must be deterministic. Okay? So this is the concept of random functions. So what about pseudorandom functions? Instead of considering that experience, which is totally random, I define a set of functions in this format. It takes 2 inputs, k and x. Both of them are n bits and generates n bits as output. But this time, I uniformly draw the first argument k at random. Okay? And fix the first argument k. It means that my function becomes something like this. K is fixed and chosen at random, uniformly at random. So I have a function like this. I can change the values of x and get the values of y. Okay? Again, how many possibilities I have here? How many types of fk's I can define? My choice is to select k at random. I have 2 to the n possibilities for k, so I have 2 to the n, not this one. This one was 2 to the n, 2 to the n. But this one is much, much, much smaller than the previous one. So I have 2 to the n possibilities. Okay? And any of these fk's is called pseudorandom if I cannot, as a adversary, cannot distinguish the challenger was selecting the function from these sets or func n sets, random functions. Okay, same template for pseudorandom distribution. On one hand, we had uniform distribution. Here, instead, we have func n, random functions, and on the other hand, on this side. And here, with this superscript notation, d of f superscript f call or f, we mean that the adversary has oracle access to the function. What do we mean by oracle access? It means that adversary can ask different values for f, but have not access to f itself. For example, you know the f, I'm the adversary. I can ask you, let me know f of x0, and you calculate and give it to me, return it to me. Okay. We have, till now, we focus only on one ciphertext. We call it ciphertext only attack. But in general, we have a stronger model of secrecy, which is chosen plaintext attack, which means that attacker has oracle access to encryption algorithm. He knows some known message, encrypted version of some known messages. He has a database. Encryption of hello is this one. Encryption of Bible is this one, etc., etc. And the thing is that for this model, CPA, if the algorithm is deterministic, then definitely it could not be CPA secure. Why? Remember the game. If the adversary has oracle access to message space, here he is going to select two messages. Then he can ask from the oracle the encrypted message, and here, if it is deterministic, then definitely this challenger guy generates the same ciphertext, and he can, for sure, he can distinguish. Yes.
But doesn't the challenger generate a new key, or?
No, the same key.
Okay, so the key stays.
He has oracle access. He don't know he don't need the value of key. The same. This guy has access to key and everything. He can compute himself. But this guy has access to someone who knows the key and can encrypt everything. Yes.
Just for my, like, intuitively, I would have expected that there exists one oracle for each key, and the attacker wouldn't know which one to ask. I think this is in the same vein.
Yeah.
Question.
No, we suppose that let's say this guy can reply to the attacker about the ciphertext. He has access to key and he can generate the ciphertext. We can consider it like this.
Okay.
Okay, and the last thing is how we can solve the second problem. So one-time pad was like this. Message space p-bit, p-bit key space p-bit. We XOR them and generate ciphertext. But this time we use a pseudorandom function. This pseudorandom function can generate a pseudorandom number for us. Okay, and the way we do that is first we select the key. Both parties know this key. Okay, and each time we select a random number. Okay, and f of k here we have key f subscript k takes r and generates a pseudorandom number. Okay. But the thing is that the other party must know R to be able to decrypt the message, because the output of F is dependent both on key and R. So then let's publish R without any limitation. So our ciphertext would be C1 and C2, such that C1 is the random number, and the C2 is similar to one-time pass, XOR of our random number with the message. Okay, for decryption, we have C2. We must XOR it with Fk of R, and R is the C1 because it is published. So we can compute, the other party can compute and retrieve the original message. To wrap up my discussion, in summary, I introduced you the symmetric key encryption concept you already are familiar with. I talked about two notions of secrecy, perfect secrecy and computational secrecy. We saw that the perfect secrecy has two intrinsic limitations. Length of the key must be identical to the length of the message, and you could use every key once. But with the aim of pseudorandomness, we defined pseudorandom number generators to solve this problem, and pseudorandom function to solve the second problem. And by the way, thank you for your attention. Okay. Thank you.
Oh, super nice.
Yeah.
Thank you.
Thank you, yeah.
And I was thinking that some of these concepts are very similar to differential privacy. They have, maybe the notation is different, but the concept is almost similar.
Same, Yes, please.
If you go one slide to the back,
Yes.
one more,
One more.
the decryption function, why doesn't it need an R?
So here, we want to XOR, we want to get rid of this, okay, to retrieve n. This must be managed. So then we must XOR this part with the same thing, Fk of R. You have K as a decryptor, but you have also you need also R.
Okay.
To be able
Yeah, right. Okay.
So what is the reason for using a randomness?
So you mean R here? What was our function? Let me just. Okay. Anyway, we here in our security game, if the algorithm is deterministic, then we know for sure that it is not CPA secure. Okay. We must somehow add a flavor of randomness. And how we add this flavor? Here we had a function which takes two inputs, K and R. Okay? K is fixed because I'm going to use it several times with my party. Okay, but every time I need this feature that my ciphertext must vary. So I select R at random to add this randomness to my scheme.
If it wasn't random, the adversary can then break that scheme that you have mentioned.
It was not CPA secure, yes. Or with this definition of secrecy, yes. Yes, please.
Would it be enough if R was unique?
What do you mean by unique?
You never, like, if you use different R's for every time you call the encryption function, like it seems to me like this is basically the non-symmetric.
Yes, exactly.
And
If it is the same, then
it should be the same. But
And could you please go to the previous slide?
yes, sure.
And so it depends. Okay, no, maybe it does not depend. So it's adversary querying this guy each time. I mean, ask something or query, and it depends how many times.
Polynomially many times, because this guy is a PPT algorithm. Okay, in all of these scenarios, the number of trials, as I already mentioned, is not exponential. And we benefit from this fact and define the negligible function. That one needs exponentially many trials to reveal something, but we know that this guy is limited to polynomially many experiences, so it cannot. Yes.
I just wanted to add that depending on the formulation of the game, K and B are not always re-rolled. Sometimes K and B are set once, but then the adversary can send a lot of pairs of messages and you recall the encryption every time and but you use the same K. But like here it looks like it does compute it every time new, but it doesn't always.
No, the thing is that, yes, you're right. The thing is that this B is selected once.
Yeah.
B is
the key as well.
Yeah. Key also, yes, definitely.
Can the attacker know R?
Attacker, so here you mean in this scheme? Yes, it is published publicly on the internet. Yeah.
Yes, what I wanted to ask, so both parties that want to talk with each other need the key, but also the pool of pseudo-random functions needs to be the same, right?
Exactly.
So you have to share the algorithm, how to generate that as well.
We have the Kirchhoff law that everything except for key is publicly known by all parties, including adversary. Yes.
Yeah, you also have to be on the XOR, right?
Yeah, this is essentially, I mean, this is one part of double redshiting, or where the first redshift is the key and the second redshift is essentially what we're looking at here. Oh.
Yes, please.
It's when you asked about just incrementing a number rather than doing random things. To go back to the game, if the adversary knew that the numbers are going to be incremented, couldn't the adversary then use the strategy of just asking for a pair of messages, retrieving, what was it? R from the answer, incrementing R, asking the oracle for that, and then using that to break the
Well,
next.
the question is whether the attacker shouldn't be able to set R. Like the R should still be selected by the challenger.
Okay, so we
Or
are
the challenger aborts if it sees the same R twice.
so we're kind of arbitrarily limiting the power of the oracle in that sense. Right, so to me it feels like either we make R random, or we say, well, the oracle is actually weaker than it could be.
In many symmetric encrypt, like if you use like normal polychacha with the random nonce, then it's not so many ciphertext because the nonce is so short. So there's good reasons for actually doing it. And I think AES-GCM has the same problem.
Good reason for doing what? Good reasons for doing what? You said it.
For using a counter. Because the possible if you
Because birthday effects and stuff.
birthday thing.
Yeah.
I think we could just stop here.
Celebrating those.
I stop here the recording.